Okay, in this section, we're going to take a very quick look at what the quantum mechanical model is talking about and how it works, at least as an introduction. Okay, so the basic idea behind quantum mechanics is this concept of waves. Okay, Erwin Schrödinger, who was probably the pioneer of quantum mechanics, and de Broglie, who we've already talked about, they figured that because of its small mass, the behavior of an electron was going to be very wave-like. And what that means is that it was going to oscillate, right? And if you kind of look at this little graphic here, we have what's called the unplucked string, which isn't moving. But if we pluck a string, a very tight string, we get this oscillation, which is a wave. Okay, and waves have wavelength, and since they have wavelength, where the wave oscillates above and below the line of where it started, we also have half wavelengths. And so a half wavelength is just from the starting position, the baseline, back to the baseline again, not crossing over it. So a full wave, one full oscillation, is actually made of two half waves. That should make sense, right? The first half wave is above the line and the second is below. Three half wavelengths is equivalent to 1 1/2 waves, full waves. It's very simple. It's no more difficult than that. Okay? So the idea then is that these electrons behave in wave-like patterns, and therefore they have wavelengths and they have half wavelengths. And what Schrödinger figured out was that in order for electrons to exist in a certain area around the nucleus, they had to exist in a pattern that was a whole number of half wavelengths. That sounds confusing, but it's really not. So if you think of the electron as oscillating, and each time it oscillates, a full oscillation is two half wavelengths. As long as we have a whole number of half wavelengths, we're fine. It's when we start to get into fractions that we have problems. Okay, so here's a little graphic that you can understand. In one particular orbital around the nucleus, one distance from the nucleus, we'll say n equals 4. That means that we have 4 full waves. Okay, so we have a full wave, and then another full wave, and then another full wave, another full wave, and everything is fine. There's no interference. At n equals 5, we have 5 full waves. Okay, so there's 1, 2, 3, 4, 5 all the way around. Everything is fine. But if we have n is equal to 4 1/3, 4 1/3 waves causes a problem. We have a mismatch of the waves. If you sort of follow the red line around, 4 full waves and then a third of another wave, we get this mismatch. It doesn't work out nicely. And what that means is there's interference. The waves, the electrons, the waves that are the electrons, they interfere with each other. And when they interfere, it sort of destroys the wave. It's sort of like if you imagine taking a jump rope and flicking it up and down to make a wave, and somebody on the other end starts doing the same thing but in a different frequency, you get this jumbled mess in the middle. And that's kind of what's happening here. And what Schrödinger then said was that if there's a mismatch, if there's interference, then electrons can't live at that distance from the nucleus. They can't be there. And so they can only be there when n is a whole number. Because when n is a whole number, then you have a whole number of half waves. And you have no interference. But when n is not a whole number, you get at this interference and the electrons can't exist there. Okay? Now Schrödinger had an equation. This is a very simplified version of the equation. H psi is equal to E psi. And just understanding a couple of things, this psi, Greek letter psi, is called the wave function. It is a very complex function that describes 3D position, three-dimensional position of an electron. Okay? The wave function has a solution called an orbital. And if you graph the solution of that function, you get a three-dimensional shape. Okay? Then there's this H thing, which is called an operator. It's a Hamiltonian. It's a set of mathematical instructions that talks about the full energy of an atom when you apply the wave function. Hamiltonian is something like a very complex three-dimensional matrix, if you're familiar with those things in math. Okay? So because this equation is so complex, it has many solutions, but every solution of this equation gives information about position, a location for each amount of energy, for each electron with a particular energy. So Schrödinger's equation was a way of figuring out where electrons are going to be based on their energy. Not in orbits like Bohr said, but now in these what are called orbitals, these areas, certain distances from the nucleus, where the waves don't cancel each other. Okay? Now, Werner Heisenberg came up with something to add to this. And this was sort of to kind of take a look at the behavior of electrons. Heisenberg had what's called an uncertainty principle, which basically said you can't know the position and the motion of an electron at the same time. Okay? The more you know about where the electron is, the less you know about how it's moving, and vice versa. Okay? So they're inversely proportional, these uncertainties. This is Heisenberg's equation. It's not really important right now, except for you to understand that that's what it's talking about. It's talking about the relationship between where it is, x, and how it's moving, m times frequency. And the fact that they're inversely proportional to one another, because they're multiplied together and they're, essentially, there's an inequality or greater than equal to this constant. It's an inverse proportional, okay? The minimum uncertainty h over 4 pi. Again, don't get too into this. Just understand the fact that this is a mathematical way of showing that as you know more about position, x, you know less about momentum, okay? So if you think about psi, the wave function itself, it doesn't have any concrete meaning. Okay, if you square the wave function, you come up with a probability of finding an electron at a certain point. It's about 90% certain. And we have this probability distribution. And if you then sort of plot this probability distribution where you use a color and you make the deeper the color means more probability, you get something called an electron density map, this reddish circle, where at the center, closest to the nucleus, we have a very high probability of finding an electron. And as we get further away from the nucleus, we have a much lower probability. It's not two-dimensional. This is spherical. And this is for hydrogen's electron. Okay? We can also plot the probability against the distance from the nucleus, and we'll see that as we get closer to the nucleus, probability is very high. As we get further away, it drops off rather quickly. So mathematically, this is just a way of saying, oh, well, this is where hydrogen's electron is going to be. It's going to be in this area around the nucleus, pretty close to the nucleus. If we were to graph it, it sort of looks like a cloud. Okay? We can break the space around the nucleus into shells. N equals 1, N equals 2, N equals 3. And if you sum up the total probability for each shell, you will find that the probability of finding an electron is greatest near the nucleus. And that the volume of each shell will increase as energy increases. So Bohr wasn't too far off thinking about these orbits. It's just they're not circular paths. They're spherical clouds where electrons will exist. Now, it's more complex than that, but that's about as far as we need to go with it for now.